Okay, everybody. Welcome back. This is going to be our third video about applications of exponential functions. And before we kick off an actual application, we're going to talk in this video about something about the coronavirus, because it's very pertinent. But before we get there, I just want to talk about the following, which is that exponential functions, we had this form for them, which is an exponential function can be written in the form f of x is equal to c times b to the power x. Now, just like equations of lines have more than one form they can come in. They can come in point-slope form or in slope-intercept form for a form of a line. We can also write exponential functions in different forms. And when we write them like this, the way we've been looking at them, the two numbers that we change are the number in front, and we also change the base. And what's interesting is that it's possible to write the same exponential function with a different base, and the effect that happens when you change to a different base, if you want to keep the same function, is that you have to multiply the x by something up here. This is just the way exponential functions work. We can talk about why at a future point. But the main point is that you can switch from one base to another, and the effect it has is on introducing a constant in front of the x up there. And there are reasons why it's helpful to us to always use one number for the base, and instead of adjusting the base, adjust instead the number in front of the x. And that's sort of equivalent to working in different bases. The base that we tend to work in is this number e, the base of the natural logarithm. It's approximately 2.718 ... It's one of those numbers like pi that goes on forever, and it's one that you're going to be running into a lot more in your future mathematics classes. So just like pi has been a big number in your classes up till now, e is going to be a big number from here on out. You're going to get to know it and get to love it. So let's get used to using exponential functions with base e. And the standard way that they look is something like this. We usually are talking here about either exponential growth, where something is getting bigger, or exponential decay, where it's getting smaller. And the typical standard form for the function is as follows. Because we're talking about things growing or shrinking, we're usually talking about time, things happening as time passes. So we tend to use t as our independent variable instead of x. So you're going to see that this has a t in it, and our function will look like this instead. F of t is equal to, it will still have a number in front. I'm going to call that number p instead. Doesn't make too much difference. And then e to the power r times t. You'll notice that this, although the letters are different, this and this are quite similar. They have a number in front. They have a base raised to a power, and the only difference is that here the base could be any number. Here the base is always the same. It's this number e, which is 2.718, and the way that we sort of effectively think of different bases is by changing this number r that's in front here, and that's called the rate, either the rate of increase or the rate of decay. So comparing these two versions, the original version of an exponential function and this version of an exponential function, here there's really two things that can change, the number in front and the base. And here there's two things that can change also, the number in front, the p, and then instead of changing the base, which we leave as e, we change this number r instead. So there's still these sort of two numbers to be determined in order to figure out one of these functions. And you're going to find that any function that you can write like this, with a little bit of futzing around, you can rewrite it like this. To write a function like this in this form, the c, that number, is just the same as the number p, so you can just copy the number there. You have to do a little calculation in order to go from the base here to find out what e to the r is equivalent to what base, but that can be done. That's not too hard. And then we just change the variable from x to t. So you guys are going to find that very, very often in the future when people talk about exponential functions, they often talk about them functions in this form. In this form, typically we have t as time. That is our independent variable. We have P, that's the initial amount. It's called the initial amount because whenever you think about things happening in time, when time is zero, that's sort of like we think of when the whole thing starts. When the time is zero, this is going to become e to the power r times zero, which is e to the power zero, which is 1. So it's like that part disappears and you're just left with p. So p is the initial value or initial amount. It's how much, if you're talking about a substance, a quantity changing over time, it's how much you have at the start. And then that r is equal to the growth rate if r is positive, or the decay rate if r is negative. Okay. So that's the basic setup, and from here on out, we're going to be looking at functions, exponential functions like this instead of like that. Oh, we may go back to this version sometimes, but it's helpful to talk about it. And I mean, really, this one is helpful if someone tells you the rate ahead of time. If they tell you what r is, you can just plug it in here directly right in front of the t. That's part of the help of doing it in this way. Also, we like having a base of e because it just works nicely for reasons that will become readily apparent in calculus. Okay, so with that in mind, let's go ahead and look at an application. This is not an example from the book. This is something more timely. This is an example that I have just come up with essentially by reading news articles. And what it's talking about is something about the coronavirus, but in particular, it's talking about how quickly the coronavirus dies, because coronavirus doesn't just live outside of a human body for very long. And in particular, they've been doing a bunch of studies. How long does it live on cardboard? How long does it live on metal or smooth surfaces? And how long does it live in the air? So, for example, when someone coughs, the aerosolized coronavirus, those molecules of the virus that are out there, how long do they survive in the air? And the idea is that any individual molecule is just like a person. Any individual person, you don't know how long they're necessarily going to survive. Any individual coronavirus molecule, you don't know how long it's going to survive. But you can get a sense of the average. And if on average this is how many coronaviruses die, or this is the chance that an individual one will die within this time, then you can figure out, based on that, at what rate the coronavirus is going to shrink. And what happens is that initially, when there's a lot of the coronavirus in the air, there are many of them dying because there are just a lot out there. And so it shrinks relatively quickly. They die quickly. Many of them die, so the number shrinks quickly. As the number gets to be fewer and fewer, well, the chances that each individual one will die are not so much. There's not as many left in the population, so there won't be as many dying. And this means that the rate at which they die is going to get smaller as the number of them gets smaller. Okay, so the example says something like, the example says this: a study published 2 weeks ago, and that was on March 17th, so really 2 weeks ago, this is very pertinent, in the New England Journal of Medicine, found experimentally that the half-life of the COVID-19 virus in the air is about 1.15 hours. What does that mean? It means that if you have a sample of COVID-19 virus, then if you wait 1.15 hours, so a little over 1 hour, then the number of virus molecules that will have survived is cut in half. And if you wait another hour and 1.15 hours, the number will be cut in half again, and then a cut in half again, etc. And the point that of any kind of virus or infectious disease is not that you have to reduce the number of viruses to zero, but that you have to reduce it to some level where it's no longer infectious, where the chances of someone catching it are very low. And I don't have the numbers for what the infectious levels are, but we're just going to proceed with this data. And I discovered through another source that when a person coughs, you can release up to about 6 billion virus molecules into the air with a single cough. And what we're going to do is consider what happens. We're going to use this information to try to consider what happens. Let's say that there's a person, they're walking out on the street, and they cough into the air. And what happens in the time subsequent to that? So, the instructions say model the number of remaining virus molecules. We're calling this V of t. That's our function. V is for virus. This is instead of using F for, because V just sort of makes sense for virus, so V of t. And suppose it's modeled by an exponential function. V of t is equal to P e to the RT. This is just our basic formula. And we want to find out what is P and what is R. Okay. And the situation we're looking at is there's someone out on the street and they have coughed into the air. Now, to consider the information that we're given, the fact that they cough 6 billion coronavirus molecules into the air initially, that tells you what the population of these virus molecules is in the air at time equals 0. So at time equals 0, there are V, that's the number of virus molecules, is equal to 6 billion. So with this in mind, we can simply plug this into our formula. Let's go ahead and do it, and let's see what we can come up with. So V of 0 is equal to 6. That's really what we've got here. And substituting this into our formula, 6 is the output. That's going to take the place of V of t. And 0 is the input. That's going to take the place of the time, t. Let's go ahead and plug it in. So we have that 6 is equal to P e to the r times 0. Now, we can simplify this thing a little bit. It's important to notice in this that there are two unknowns. There's r, we don't know what that is, and there's p, we don't know what that is. But this number e, we do know. This is the number 2.718. It's just a constant. Now, we're going to leave it as an e. I just wanted to remind you so that you don't think that we have to find what e is equal to. We know what that's equal to. Now, what I can simplify here is in the exponent, r times 0 is just r. So this is 6 is equal to p e to the 0. And e to the power 0, any number except 0 itself, to the power 0 is going to be equal to 1. So we can cancel out this guy is equal just to 1. So what do we have? We have that 6 is equal to p. We found p. And so what we know is that our formula for the number of these molecules remaining in the air, it looks like this: 6e to the rt. And what we don't have is we don't have r. That's what we're missing here. And if you look back, we also don't have any other input and output pair. For example, if the problem had given us at some point in the future, for example, when the time was equal to, say, 3 hours, then there were now 2 billion coronavirus molecules or something of that nature, then we would have another pair. We would be able to write V of something equals something. Again, we would be able to figure it out. Okay, but unfortunately, we're not given that. What we are given, which we haven't used, is the half-life. And the half-life is how long it takes for the amount to be cut in half. So half-life is 1.15 hours. And that means that after 1.15 hours, V is cut in half. Now, V started when time was equal to 0. We had that V of 0 was equal to 6. And the idea is that if we wait 1.15 hours, so at time equal 1.15, well, the number of viruses left, V at that time, 1.15, will be half as big. It'll be equal to 6 over 2. It's cut in half, which of course is 3. And this somehow gives us a new time, 1.15, and a new number of viruses, 3 billion. So we can substitute this in as well, plug in. And plugging this one in, we should be able to figure out our missing value, which is r. Let's go ahead and do it. If we plug this in, what we get is the output is 3, and that is equal to 6 times e to the r times 1.15. So this says 3 is equal to 6 e to the r times 1.15. And we want to find that r. Once again, this is annoying because there's these decimals running around, but other than that, these are just numbers, and we're going to solve them using algebra the same way that we did before, just keeping track of the numbers, and then in the end, let a calculator worry about dealing with those decimals. Okay, we want to get this number r by itself. To get r by itself, going to have to get rid of a few different things. In particular, we're going to have to get rid of the 6, and that one's easy. We can just divide both sides by 6. So let's see, we divide by 6 here and here. On the right-hand side, it cancels, and we just have e to the, I'm going to write it, instead of r times 1.15, I'm going to write it as 1.15r. And then on the left-hand side, 3 over 6 is the same as 1/2. Okay. We're now once again in a position of having an equation where the only variable that's left, is this guy r up in the exponent. And in order to deal with that variable in the exponent, we're going to use the same trick, which is to take the natural log of both sides. Now, natural log of 1/2 is equal to natural log of e to the power 1.15r. We're going to leave the left-hand side alone. That's just, we're going to stay as natural log of 1/2. On the right-hand side, we're going to once again use the rule that says any logarithm which has something to a power inside, you can bring the power out into the front. And so we get, and here we have to be careful to bring the entire power, 1.15r. So this is 1.15r ln of e. That's the only thing that's left. Now, we're getting close to done here. We just need to isolate this r. And to do it, what I'm going to do is I'm going to divide both sides by the numbers that that are next to r. So I'm going to divide both sides by 1.15. And I can also divide both sides by this natural log of e. The 1.15 and the ln of e are connected by multiplication on the bottom because I'm dividing by both of them. Okay. On the right-hand side, everything cancels except for the r. On the left-hand side, we have this slightly messy-looking expression, natural log of 1/2 over 1.15 natural log of e. Now, I could just plug this into a calculator, that's fine, but I want to make one observation, which is we don't typically know what the natural log of a lot of different numbers are just off the top of our heads. We use a calculator for it. But there's one value which, when you take the natural log of it, it gives you an easy answer, and that is the natural log of e. Remember, the natural log is the log in base e, and the log in base e is like saying e raised to what power gives you e, and the answer is 1. So if you followed that, awesome. If you didn't follow it, then this is sort of a good fact to have memorized, which is the natural log of e is equal to 1. Similarly, the log in base 10 of 10 is equal to 1. Those are handy facts. And so that ln of e I'm just going to get rid of altogether. That's just equal to 1. So this is natural log of 1/2 over 1.15. And that's equal to r. Let's go ahead and plug this in to a calculator and see what we get. So this is, let's see, natural log of 1/2 divided by 1.15. And that's equal to negative 0.6027. I'm going to keep 3 decimals, which means it'll be negative 0.6027. 0.603. Negative 0.603. So r is approximately equal to negative 0.603. So, if you recall, what we're working on is we're trying to find a formula, this formula. We're trying to fill in the value of p, we did that already, that was 6, and the value of r we just found now, it was negative 0.603. So let's go ahead and put those in, and this will give us our overall formula for v of t. It's 6 times e to the negative 0.603 t, where v is the number of COVID-19 molecules in billions remaining at time t is the time in hours. How did the time get to be in hours? Well, we were first given that half-life of 1.15 hours. And what's nice is that this formula will allow us to predict, if we imagine this scenario, someone is on the street, they cough, and they introduce 6 billion coronavirus molecules into the air. As time passes, that number is going to drop off. Those virus molecules are not going to survive. And this tells you what the population is going to be, how many will be left at any given time in the future. Okay. Something I want to notice, the rate that we got, the r, is a negative rate. And I just want to draw a little contrast here between the two forms of an exponential function. Here, the form that we're looking at, function is equal to p times e to the rt. Here, the rate r, it's the number in front of the t, and we say that it's either a growth rate if r is bigger than 0 or a decay rate if r is less than 0. And this one, first of all, is negative. R is negative, so that's a decay rate. That means that the amount is getting smaller over time. That's what we call exponential decay. And also, just worth noting that this number, the r, could be positive or negative. And that's in contrast when we were dealing with a base b. The base b was always positive. And here the importance was whether it was bigger than 1, that means there was growth, or between 0 and 1, that means it was decay. Here, when you translate that base into e to the power rt, the r either comes out positive for growth or negative for decay. So this one, since the decay rate, that r is negative, we say that this is modeling exponential decay. Okay. The next question that we're asked is how many of the virus molecules will remain viable? Viable just means alive or able to cause infection 5 hours after the person's cough. So you see someone on the street, they cough, it goes into the air. 5 hours later, how many coronavirus molecules are there left? For this one, well, we now have a formula that tells us for any time t, how many are left, and it's just simply given by this v of t. So part B is asking what is v of 5 equal to? And we can find this out by plugging 5 in for t and then doing the calculation. What I'm going to do is go ahead and put into Desmos just the entire formula v of t so that we can refer to it later. And it's 6e to the negative 0.603 t. Let's go ahead and do it. So let me see. This is going to be v of t is equal to 6 e to the power negative 0.603 t. Now, some things to note. Let me give myself a little pointer here. Give me just 1 sec. Okay, so now I have a little point I can drag around here. Please ignore the little sliders moving on the left there. You'll see this is a graph of the population. Here is time along the bottom, that's t, and when t is 0, the population is 6, measured in billions, so that's 6 billion right there. And you'll see that although the population starts high, it drops off quickly, and by the 5-hour mark, it is much, much smaller than it was before. Indeed, it looks like, let me see, if this is 6 billion, 5, 4, 3, 2, less than a billion, less than half a billion, it's really reached down into the, so half a billion is 500 million. It's going to be even less than that. So the number of those has dropped off dramatically. It may still sound like a lot to say 500 million virus molecules, but when you're dealing with things on the size and scale of viruses, you need a lot of them together in order to have any assurance that infection is going to be passed on, which means reducing the total number is a very effective way of reducing the chance of infection. So let's take a look. It looks like at the 5-hour mark, we would want to plug in to our formula. We would like to plug in the number 5 for t, and we can do that here just using the notation that we established already. Our function is v, and we want to put in v of 5. And what is v of 5? It's equal to 0.294, and I'm just going to round that off to 0.29. Let's go back. We'll record that. This says that, v of 5 from Desmos is approximately equal to 0.29. Now, 0.29 what? The idea is that we're measuring the V, the number of molecules left, in billions. So 0.29 billion molecules. So far less than a billion, about a quarter of a billion. And that's, if you're interested in actually knowing the number, this is 290 million molecules left. Great. So this says that after 5 hours, the number has reduced from 6 billion to 0.29 billion, or to 290 million. That is our answer to part B. Now, you may find that distressing or not. To me, the actual numbers, since they're large and I don't have a good intuition for large numbers, they're hard to handle. But the part of this that makes it, that resonates with me, is when we look at that graph and we see the steep way in which it shrinks in the beginning. Now, it's true that some of those molecules hang around for a long time after that. That's true. But the vast majority of them disappear in the first couple of hours' time. All right. And then the final question is... Oh, by the way, it's worth noting, I just looked up this information and made up these questions, but I do not yet know what the answers to these are. I'm discovering them with you. So I did not know what the total was going to be after 5 hours, that it came out to 0.29. We're going to see also what is the total going to be here. How long will it take for the number of remaining molecules to reach 6 million? Yeah. 6 million is 0.1% of the original amount, and it's a little tricky. We're going to somehow have to deal with the fact that I annoyingly gave it to this in million instead of billion. So let's see. This is part C. Whoopsie. When will V reach 6 million? Now, one of the things that we're going to need to do in order to use our formula, since our formula interprets v in billions, is we're going to need to convert millions into billions. And if you happen to know that the way that you get from millions to billions is by adding 3 more zeros, that might be a good suggestion of what we need to do here. If we have 6 millions, well, you can think about how many is that in billions. It's going to end up being a much smaller number in billions. 6 million is way less than a billion. And the fact that you add 3 zeros on to get from millions to billions says to me something with powers of 10 and moving the decimal 3 places. So, of course, you can do this more formally, but just informally, if 6 million is our starting number, if we want to change it to billions, we're going to move it 1, 2, 3 spaces, and then we're going to change it to billions. And what does that give us? 6 million is 0.006 billion. And what did we do? We did it by moving the decimal 3 places over. So our question now becomes, when will v of t equal 0.006? And now it's given in the correct units in billions. So v of t equal 0.006 billion, question mark. Well, what do? We have a formula for v of t. Of course, our formula is the one in the box at the top. And we're just going to replace v of t with that 0.006, and then leave the rest of it in there and solve that resulting thing for t. I encourage you to do that. Replace this with 0.006 here and see if you can get t by itself. Feel free to use a calculator or use Desmos or some other computational tool if you wish. Go ahead and do that now, and then come back and we'll work through it together. Okay, so here we go. We're replacing v of t with 0.006, and that's equal to 6e to the negative 0.603 t. And we want to solve for t. We want to get that t by itself. How do we do it? Well, once again, we're going to start by dividing both sides by 6. So we're going to get 0.006 over 6 is equal to e to the minus 0.603 t. The next thing that we're going to want to do, because we have our variable is stuck up in the power, is we're going to take the natural log of both sides. So the natural log of this 0.006 over 6 is equal to the natural log of e to the minus 0.603 t. Next, we use the rule of logs, which says that a log of something to a power, you can move the power out in the front. So keeping the left-hand side the same, on the right-hand side we have negative 0.603 t natural log of e. Now, we talked about the natural log of e before. The natural log of e is just equal to 1, so we can get rid of it. And that leaves us just with negative 0.603 t is equal to, and then this natural log on the other side. And so to get t by itself, I'm going to divide both sides by that negative 0.603, divide by that negative 0.603. On the right-hand side, the numbers on the top and bottom cancel, leaves us with just the t. And on the left-hand side, well, we have this expression. It's the natural log of 0.006 over 6, and then over negative 0.603. For this, we're going to use Desmos to do it. And for this one, let's see. This is the natural log of 0.006 divided by 6. And then that whole thing divided by that negative 0.603. And what do we get? Well, we get 11 let's say 46. 11.46. So t equal 11.46. And what is t measured in? It's 11.46 hours. So this says, how long is it going to take if we imagine this person coughing on the street? They're infected with coronavirus. They send 6 billion of these molecules out into the air. How long will it take for that number to be reduced, not to 1/10 or 1/100th of its original size, but to 1/1000th of its original size? That is 0.1%. And the answer, it will take almost 12 hours. So if someone went out, if this happened at, say, 11 o'clock in the morning, then by 11 p.m. at night, the number of remaining virus molecules viable and in the air would have been reduced by a factor of 1,000. It would be 0.1%, the original amount. Now, this does not, of course, tell the whole real-world story. Disease transmission is much more complicated than this, and it depends on a lot of things like, do all of those virus molecules sort of stay in the air and in one place? Do they disperse? Do they land on things? Do they have a different lifespan once they've landed on a substance? That is generally true. Some substances, they last longer. Sometimes they last less long. So on the one hand, this is not supposed to be something that you use to make your plans for the day, but it is illustrative of the way that exponential decay works. All right, thanks everybody.